Hello everyone, welcome to the lecture series on computer architecture and organization. In this, we are going to see about this introduction to graphics processing unit. The introduction to graphics processing unit is that the original justification for adding this SIMD instructions to existing architectures was that many microprocessors were connected to graphics displays in PCs and workstations, so an increasing fraction of processing time was used for graphics. As Moore's law increased the number of transistors available to microprocessor, it is therefore made sense to improve this graphics processing. A major driving force for improving graphics processing was the computer game industry, both on PCs and in dedicated game consoles such as the Sony PlayStation. The rapidly growing game market encouraged many companies to make increasing investments in developing faster graphics hardware, and this positive feedback loop led graphics processing to improve at a faster rate than the general purpose processing in mainstream microprocessors. Given that the graphics and game community had different goals than the microprocessor development community, it involved its own style of processing and terminology. As the graphics processor increased in power, they earned the name graphics processing units or GPUs to distinguish themselves from CPUs. For a few $100s, anyone can buy a GPU today with hundreds of parallel floating point units, which makes this high performance computing more accessible. The interest in GPU computing blossomed when this potential was combined with a programming language that made GPUs easier to program. Hence, many programmers of scientific and multimedia applications today are pondering whether to use GPUs or CPUs. So, these are all the key characteristics of GPUs. So, GPUs are accelerators that supplement a CPU, so they do not need be able to perform all the tasks of a CPU. This role allows them to dedicate all their resources to graphics. It's fine for GPUs to perform some tasks poorly or not at all, given that in a system with both a CPU and a GPU, the CPU can do them if needed. The GPU problem sizes are typically hundreds of megabytes to gigabytes, but not hundreds of gigabytes to terabytes. These differences led to different styles of architecture. Perhaps the biggest difference is that the GPUs do not rely on multi-level caches to overcome the long latency to memory as do CPUs. Instead, GPUs rely on hardware multithreading to hide the latency to memory. That is, between the time of a memory request and the time the data arrives, the GPU executes hundreds or thousands of threads that are independent of that request. The GPU memory is thus oriented towards the bandwidth rather than the latency. There are even special graphics DRAM chips for GPUs that are wider and have higher bandwidth than DRAM chips for CPUs. In addition, GPU memories have traditionally had smaller main memories than the conventional microprocessors. In 2013, GPUs typically have 4 to 6 GB or less, while CPUs have 32 to 256 GB. Finally, keep in mind that for general purpose computation, you must include the time to transfer the data between the CPU memory and the GPU memory, since the GPU is a coprocessor. Given the reliance on many threads to deliver good memory bandwidth, GPUs can accommodate many parallel processors as well as many threads. Hence, each GPU processor is more highly multi-threaded than a typical CPU, plus they have more processors. So this is the simplified block diagram of the data path of a multi-threaded SIMD processor. So this has 16 SIMD lanes, that is, these are all the SIMD lanes that are the thread processor. The SIMD thread scheduler has many independent SIMD threads that it chooses from to run on this processor. So an introduction to NVIDIA GPU architecture. So unlike most vector architectures, GPUs also rely on hardware multithreading within a single multi-threaded SIMD processor to hide the memory latency. A multi-threaded SIMD processor is similar to a vector processor, but the former has many parallel functional units instead of just a few that are deeply pipelined as does the latter. As mentioned above, a GPU contains a collection of multi-threaded SIMD processors. That is, a GPU is a MIMD composed of multi-threaded SIMD processors. For example, NVIDIA has 4 implementations of the Fermi architecture at different price points with 7, 11, 14, or 15 multi-threaded SIMD processors. To provide this transparent scalability across models of GPUs with different number of multi-threaded SIMD processors, the thread block scheduler hardware assigns blocks of threads to multi-threaded SIMD processors. Dropping down one more level of detail, the machine object that the hardware creates, manages, schedules, and executes is a thread of SIMD instructions, which we will also call a SIMD thread. It is a traditional thread, but it contains exclusively SIMD instructions. These SIMD threads have their own program counters and they run on a multi-threaded SIMD processor. The SIMD thread scheduler includes a controller that lets us know which threads of SIMD instructions are ready to run, and then it sends them off to a dispatch unit to be run on the multi-threaded SIMD processor. Hardware schedulers. It is identical to a hardware thread scheduler in a traditional multi-threaded processor, except that it is scheduling threads of SIMD instructions. Thus, GPU hardware has two levels of hardware schedulers: the thread block scheduler that assigns blocks of threads to multi-threaded SIMD processors, and the SIMD thread scheduler within a SIMD processor which schedules when SIMD threads should run. The SIMD instructions of these threads are 32 wide, so each thread of SIMD instructions would compute 32 of the elements of the computation. Since the thread consists of SIMD instructions, the SIMD processor must have parallel functional units to perform the operation. We call them SIMD lane. And this is about this NVIDIA GPU memory structures. Here, the GPU memory is shared by the vectorized loops. All threads of SIMD instructions within a thread block share, that is this local memory. So this figure shows about the memory structures. We call the on-chip memory that is local to each multi-threaded SIMD processor. They are called as local memory. It is shared by the SIMD lanes with a multi-threaded SIMD processor, but this memory is not shared between the multi-threaded SIMD processors. We call the off-chip DRAM shared by the whole GPU and all thread blocks GPU memory. Rather than rely on large caches to contain the whole working sets of an application, GPUs traditionally use smaller steaming caches and rely on extensive multi-threading of threads of SIMD instructions to hide the long latency to DRAM. Since their working sets can be hundreds of megabytes, thus they will not fit in the last level cache of a multi-core microprocessor. Given the use of hardware multi-threading to hide DRAM latency, the chip area used for caches and system processors is spent instead on computing resources and on the large number of registers to hold the state of the memory threads of SIMD instructions.